Welcome to Math TV with Professor V. In this video, we're going to look at 4 examples of how to evaluate integrals using trigonometric or trig substitution. I'll link the introductory lecture video on this topic here. So if you haven't watched it already, be sure to check this video out because I walk you through the setup with a lot more basic examples and help break down the concepts a little bit further. So just to summarize, there's 3 different cases in which you're going to use trigonometric substitution. Usually the integrand will involve a radical, but it doesn't have to. The first case is if you see an expression of the form a squared minus x squared. So a is a constant, you got the constant squared minus the variable squared. In that case, you use the substitution where you let x equal a sine theta. Case 2, the integrand has an expression of the form a squared plus x squared. So in that case, you'd have a constant squared plus variable squared. This time you want to use the substitution x equals a tan theta. And then the third case is the integrand has an expression of the form x squared minus a squared. And in that case, you want to use the substitution x equals a secant theta. So just keep in mind when you have addition, right, between the constant squared and the variable squared, that's when you use tangent. And then just check the order of subtraction when you're deciding between sine or secant. If it's the constant first, then you use sine. If it's the variable first, that's when you use secant. If you pick the wrong substitution, then the trigonometric identity won't work in a way to help you simplify and you'll get stuck anyways. But if you choose appropriately the first time, then you won't run into those sorts of problems. So let's dive right in. First example I have for you is basically using case 1 substitution. So we've got here integral y squared over 16 minus y squared raised to the 3/2 dy. All right, so I know this is going to match up with case 1 since I have a constant 16 minus y squared, the variable squared. And in this case, a is equal to 4, right? Since 4 squared is 16. So what I'm going to do is let y equal 4 sine theta. Very nice. Next step, we want to figure out what dy is. So let's differentiate both sides here. Dy is going to equal 4 cosine theta d theta. So now let's substitute everything into the integral. So we have all of our terms using theta, no more y's. Here we go. So in the numerator, instead of y squared, I'm going to have 4 sine theta squared. In the denominator, we have, again, 16 minus y squared. So that's 16 minus y squared is going to be 16 sine squared theta to the 3/2. And then lastly, dy is 4 cosine theta d theta. So here's dy. Here's dy. Here is my y squared. Okay, and then the denominator you can see here. Let me just underline it so it doesn't get too messy. Okay, now let's clean it up. So check out the numerator. We've got 4 sine theta, that whole thing squared. So that's going to be 16 sine squared theta. And then I'll just put the 4 cosine theta right next to it for now. Just for now, over, and then watch how we're going to simplify the denominator. So the whole point of making the substitution is because of the lovely identity we get to use right now. I'm going to factor out that 16, and then I have 1 minus sine squared theta, and all of this is raised to the 3/2 power. And never forget your d theta. Okay, looks good. The whole point now is that I can replace 1 minus sine squared with what? Very good. That's cosine squared theta. Okay. And so now let's see what we have going on. Let's clean up our constants. Yeah, we've got a 16 times 4, so that's 64. Sine squared theta, cosine theta, over. Now be careful here. You see this 3/2 exponent that distributes or applies to both the 16 and this cosine squared here. So we're going to have 16 to the 3/2 and then cosine squared theta to the 3/2 d theta. All right? Very nice. Okay, hopefully some things will cancel out nicely here. 16 to the 3/2. Don't get your calculator out, please. Don't even think about it. When you raise some number to the 3/2 power, first you take the root that's in the denominator. In this case, I'm going to take a square root. So square root of 16, that's 4. And then I raise that number to the numerator. So 4 cubed is 64. Okay, so 16 to the 3/2, that's 64. And you see how we have a 64 in the numerator too? Oh, fabulous. So just cancel, cancel right there. And then similarly, if you have cosine squared theta raised to the 3/2, think about it this way. If you have, say, x squared raised to the 3/2, think about your laws of exponents. Back when you were a sweet little algebra student, you multiply those exponents. So 2 times 3/2, that's just going to be 3, right? You would have x cubed. So similarly, this cosine squared theta raised to the 3/2 is going to be cosine cubed theta. Okay, cool. Now let me cancel out what I can. So I have no more constants, right? The 64s are gone. And then we're going to have integral sine squared theta, cosine theta, over cosine cubed theta d theta. Anything else you notice? I hope so. So you can cancel out the cosine from the numerator, and now you only have cosine squared in the denominator. And we have here sine squared theta over cosine squared theta. Okay, since we're going to try to integrate, let's see what we want to do with this. Well, sine squared theta over cosine squared theta, maybe your brain hops to tangent squared theta, which is good. It is tangent squared theta. But do we know the antiderivative of tangent squared theta? Maybe not, right? It's not one of the straightforward, obvious ones that you memorize early on in your calc career. So instead, we're going to replace tangent squared theta using a Pythagorean identity. Remember, tangent squared theta is equal to secant squared theta minus 1 d theta. You just have to memorize all of those. And then from here, we're home free because we do know the antiderivative of secant squared, right? We memorized all those back in Calc 1. Antiderivative of secant squared theta would just be tan theta minus antiderivative of 1, just theta. Very good. Plus c. So now you put plus c since we anti-differentiated. Okay, almost done. Just remember, the original integral was expressed in terms of y, not theta. So we have to go back to the original variable. So go back, check what that original substitution was that you made. You remember right here when we let y equal 4 sine theta? That's going to help us switch back to the original variable. So remember or recall that y was equal to 4 sine theta. So what we're going to do now is isolate the trig function, isolate sine theta. Sine theta equals y over 4. And we're going to draw a triangle that represents this, right triangle, SOHCAHTOA time. So sine theta, that's the ratio of the opposite side over the hypotenuse. So that's going to be y over here. 4 is the hypotenuse. And then just use the Pythagorean theorem to find the missing side. In this case, it's going to be rad 16 minus y squared. And just as a clue, this expression for the missing side should match something that you saw in the original integral, which we did, right? We had 16 minus y squared in the denominator. Do you remember? It was so long ago. Right here. 16 minus y squared. Okay. Now we're going to go back and rewrite everything in terms of y. So tangent of theta, we know tangent is the ratio of the opposite over adjacent side. So check out your triangle. Here's the opposite side, here's the adjacent side. So tangent of theta is going to be y over rad 16 minus y squared minus, and then what do we do with plain old theta? It's not bad, don't worry. Remember here, sine of theta equals y over 4. That means theta, just plain old theta, is equal to sine inverse of y over 4. So that's what I'm going to write instead of theta. Substitute that in. That's sine inverse of y over 4, and then plus c. So that is our final answer. All right. Good. Not too bad, hopefully. You do have to make sure that you have those Pythagorean identities memorized. Otherwise, you're going to get stuck, or you might substitute something in incorrectly and mess up the whole problem. Okay, ready for another example? Let's check out one that involves case 2. So example 2, we have integral here of radical x squared plus 36 over 9x squared dx. So I already told you it was case 2. It doesn't matter what number the case is. I mean, who cares? But what you want to look at is we have a variable squared plus a constant. So that calls for tangent. And a in this case is equal to 6, right? A squared is 36, so a is 6. So I'm going to let's let x equal 6 tangent theta. And then the next step's always the same. You're going to find dx, which would be 6 secant squared theta d theta. All right, that's all the prep work that we do. Now we're going to substitute everything back into the integral, rewrite it using thetas only. So we have here integral. In the numerator, we've got x squared plus 36, so that's going to be 36 tan squared theta plus 36 over 9x squared, so that's 9 times x squared would be 36 tan squared theta, and then dx is 6 secant squared theta d theta. Beautiful. Now, once you get more comfortable, maybe you'll start skipping some steps, but I'm going to break everything down. I won't skip a single thing for now. So we've got in the numerator radical 36 times tan squared theta plus 1. You always factor out that constant over, I'm just going to leave these as is for now. You'll see why. 9 times 36 tan squared theta times 6 secant squared theta d theta. Okay, now the whole point of factoring out the 36 is so that now we can replace tan squared theta plus 1 with secant squared theta. So we've got 36 secant squared theta all underneath the radical in the numerator. And like I explained in the introductory video, if you watched it before this, remember technically this is 6 absolute value of secant theta, but because we restrict theta, we don't have to worry about keeping the absolute value. We keep theta only where secant's going to be positive. Okay, so what does that mean for us now? Well, we can replace the numerator with square root of 36, which is just 6 secant theta. And then remember, we've got over here another 6 secant squared theta. So I'll just put that together in the numerator with it. So 6 secant squared theta, that's all in the numerator. And then we've got 9 times 36 tan squared theta d theta. All right, let's cancel out 6 times 6 with the 36. Love it. And then that pesky little 9, let's exile it outside of the integral. So I always like pulling the constants out so I can just focus on what I'm trying to integrate. In the numerator, we've got secant cubed theta. And in the denominator, we've got a tan squared theta d theta. Okay, so now you're going to have to think back to one of the previous lessons where you learned how to deal with trigonometric integrals. And most of the cases that we worked with have to deal with if the power on secant is even or if the power on tangent is odd, how to break it up appropriately. But you might be noticing that this is tricky because we've got the tangent squared in the denominator and we have a secant cubed in the numerator. So you can't let u equal tangent theta, no, because du would be secant squared theta d theta, and then you've got an extra secant that you're stuck with, you know. So when you're kind of at this, you know, standstill, you can't figure out what to do, my recommendation is rewrite everything using sines and cosines, all right? And see if maybe you can clean things up and then proceed from there. So that's what we're going to do. I've got 1/9 integral. Now check this out. Secant cubed, that's going to be 1 over cosine cubed theta, right? So we've got 1 over cosine cubed theta. And then we have a tangent squared, but it's in the denominator. So tangent is normally sine theta over cosine theta. It's going to be the other way around, and it's going to be squared. So we're going to have cosine squared theta over sine squared theta d theta. Okay. Now I notice I can cancel out cosine squared in the numerator, and I'm just going to have 1 power of cosine in the denominator. Very excited. Looks like things are cleaning up. So we've got 1/9 integral 1 over cosine theta times sine squared theta d theta. But now maybe you're stuck again. We can't do a u sub because if I try to let u equal sine theta, my cosine theta is in the denominator. It's not in the numerator, so that won't work. Vice versa won't work. So it feels like we're stuck again. Okay, let's break things up, see if we can use some other trig expressions. And I'm going to rewrite things. Instead of 1 over cosine theta, all right, this is going to become secant theta. And then instead of 1 over sine squared theta, I'm going to replace that with cosecant squared theta d theta. Okay, this is still not looking good, but I am moderately excited because we've got a cosecant squared. We don't easily know the antiderivative of cosecant squared, but I can use a Pythagorean identity to rewrite it. And if you're just struggling right now really hard with all the trig, this is what you need to do. Remember sine squared theta plus cosine squared theta equals 1. I mean, if you can't remember that, I can't help you. But from here, say you need the identity with cosecant squared and you don't remember what it is. Well, cosecant squared is 1 over sine squared. So I'm going to divide everything here by sine squared. All right, and then notice we have 1 plus, this is cotangent squared theta, is equal to cosecant squared theta. So I'm going to go ahead and replace cosecant squared theta with 1 plus cotangent squared theta. And then we've still got that secant theta and the 1/9 all hanging out. Ooh, okay. Can we do anything now? We're going to distribute the secant theta and split this into 2 integrals, all right? So we've got 1/9 times, let's do it like this, integral secant theta d theta plus integral secant theta cotangent squared theta d theta. I'm going to call this integral 1. I'm going to call this integral 2. Take a step back, make sure you are hanging in there. This is an exceptionally tricky one. That's why I'm doing it for you guys. Okay. Integral number 1. Antiderivative of secant theta d theta. What is it? Oh, this one you should just memorize. Yes, it's ln, absolute value, secant theta, plus tan theta, plus, I'm going to say c1. Okay, we've got a constant there. Now for the spicy part, integral number 2. We've got secant theta, cotangent squared theta, d theta. Again, mixing secants and cotangents isn't typically one of the integrals that we have like a set technique for. So that's why I'm going to think, let's rewrite using sines and cosines again. Maybe something fabulous will happen. Who's to say? So secant theta, that's 1 over cosine theta. Cotangent squared theta, well, that's in the denominator. So this time that's the same as tangent squared theta. So this is going to be, oh no, it's not in the denominator. What am I saying? It's just cotangent squared theta. So it's going to be cosine squared theta over sine squared theta d theta. And ooh la la, this cosine theta cancels out. And now I'm happy because I finally have a trig function in the numerator. That's all we wanted this whole time. I just wanted someone in the numerator so I can just do a u sub, for crying out loud. Do you see what we should let u equal? Okay, should it be sine theta or should it be sine squared theta? It should just be sine theta, right? You're going to let u, don't put the exponent on when you're making a u sub for a trig function, okay? Just let u equal sine theta, then du would be cosine theta d theta, which I have there, voila. Why would u being sine squared theta be a bad choice? Because remember, sine squared theta, when you differentiate it to find du, you have to use the chain rule. So it would be 2 sine theta cosine theta d theta, which we don't have. Bad choice. So typically when you u sub for these trig functions like this, don't put the exponent in. You're just going to have u squared in the denominator, which is no big deal. But look how nice and clean du is now, right? Good, good. Okay, so we've got integral now du over u squared. If you want to remind yourself, this is integral u to the negative second du. Add 1, divide by the new exponent, so it's going to be negative u to the negative first, which is the same as 1 over u, plus I'm going to write c2. Okay, and then remember, u was sine theta, so this is negative 1 over sine theta plus c2. All right, so putting everything together, what do we have? Well, look back. Remember when I broke it up into integral 1 and 2, I still had a 1/9 sitting outside of everything. Okay, so we got to put that 1/9 back. Put the 1/9 back. We have 1/9 times ln, absolute value, secant theta plus tan theta, got all that, minus 1 over sine theta. Okay, and then I'm going to put plus k. Why the heck am I using k? You'll see. So in here I had c1 plus c2, right? If I put my constants together, but then I multiplied by 1/9. So if we're going to be very precise, which we always are, I'm going to say k equals 1/9 times c1 plus c2. Okay. Now, remember, we have to rewrite everything in terms of x. And remember, we let x equal 6 tan theta, so it's triangle time. That means x over 6 is equal to tan theta. So let's draw a triangle. Here's theta. Tangent of theta is going to be the ratio of the opposite over adjacent side. So find the hypotenuse, Pythagorean theorem time, it's x squared plus 36. Lovely. So let's substitute everything back in now. We have 1/9 times natural log, absolute value, secant theta. So remember, cosine theta is adjacent over hypotenuse. So secant theta is the reciprocal. It's hypotenuse over adjacent. Hypotenuse is rad x squared plus 36 over 6 plus tan theta, that's x over 6. Bam. Minus 1 over sine theta. So that's reciprocal of sine theta. Sine theta is ratio of opposite over hypotenuse. So this is going to be hypotenuse over opposite. So rad x squared plus 36 over x. And then I've got my plus k. Okay, now you might be thinking, this looks lovely as is. I feel so done. This took forever, but we can be more precise, more succinct. Okay, we've got this 1/9 hanging out here. I'm going to combine these two terms because notice they have the same denominator. So I can write this as ln absolute value radical x squared plus 36 plus x over 6 minus square root x squared plus 36 over x plus k. And oftentimes you'll see the following property of logarithms used to further simplify. So remember, if you have natural log of a divided by b, you can rewrite it as ln of a, the numerator, so rad x squared plus 36 plus x minus ln of b, ln of the denominator, which is 6. And then I still have 1/9 in the front minus rad x squared plus 36 over x plus k. What's the point of doing that? Well, a lot of the times you'll see this is just some constant, right? The minus ln of 6 times 1/9 technically. We'll just absorb it into the constant and not write it in our final answer. So as the most aesthetically pleasing cleaned up final answer, we should have 1/9 ln absolute value rad x squared plus 36 plus x minus, and I'm actually going to distribute the 1/9 to that next term, rad x squared plus 36 over 9x plus c. Ooh, so who is this c? This is getting spicy now. Let's be precise, okay? Well, c was k combined with negative ln of 6 over 9, right? So c is equal to k minus ln of 6 over 9. And that's it. This was definitely a tricky integral. There may be another way to evaluate it more easily. So play around with it. If you come up with something better, let me know. I'd love to hear it. But it took, took some work for sure. They won't be all this spicy. Have no fear. Okay. We still haven't looked at a case 3 example, so that's coming in next. I already gave away the surprise though, huh? You already know it's going to be a case 3 substitution. Oh well, so we've got dx over radical 25x squared minus 121. And then they tell you, P.S. x is greater than 11 over 5. So you don't have to worry that you're going to have an expression underneath the square root sign that's negative. How considerate of them. Okay, we haven't looked at one yet where there's a coefficient on the variable term. And remember, all the substitutions just had a 1 in front of the x squared. So in your mind, you basically just factor it out, and then you would have x squared minus 121 over 25. You see that? So remember this constant term here, that's your a squared. So that means a is equal to 11 over 5. Since we have the variable squared minus the constant, that's the case where we're going to use secant theta for the substitution. So we're going to let x equal 11 over 5 secant theta. Okay, then that means dx is 11 over 5 secant theta tan theta d theta. Beautiful, love it. Now let's go back and substitute everything back in. So our integral is now going to be in terms of theta. Instead of dx in the numerator, I've got 11 over 5 secant theta tan theta d theta over square root 25 times x squared. So we're going to square 11 over 5 secant theta. Square it with caution. 11 squared, 121. 5 squared, 25. Then you have secant squared theta minus 121. Okay, things are looking good, aren't they? I'm so proud of us. So 25s cancel. Bam, bam. And then let's go ahead, take that 11 over 5 outside so it harasses us no longer. And then we've got secant theta, tan theta, d theta over radical. Are you guys good if I just take the 121 out now? That's what you're going to do every single time you factor out that constant. So let's get this ball rolling. We've got 121 times secant squared theta minus 1. Love it, love it. Now let's see here. Secant squared theta minus 1, that's equal to tangent squared theta. Okay, cool. So now what do we have? We've got 11 over 5 sitting outside minding its own business. Secant theta, tan theta, d theta upstairs. And then in the denominator, I've got square root of 121, so that's 11. And then square root of tan squared theta. Remember, we restricted theta to be only where tangent is positive, so we don't have to worry about absolute value. So you can just write tan theta with a clean conscience, okay? Whew. Okay, now it's cancel party time, my favorite time. 11s are gone. Bam, bam. Tangent theta is also gone. Hooray! And now we just have a 1/5 secant theta d theta. Oh, you guys, we're home free. We know this antiderivative. We know this one. We memorized it. It's ln, absolute value, secant theta plus tan theta plus c. Yeah, you just got to suck it up and memorize it. If you don't remember where it came from, I'll link the video here where I show you how to derive it. But honestly, it comes up so often, you just need to memorize it, okay? All right. Now, remember, original integral was not in terms of theta, it was in terms of x, so it's triangle time. And if you'll remember, we let x equal 11 over 5 secant theta. So always isolate the trig function, all right? So that means secant theta equals 5x over 11. So we'll use that to fill in the sides of the triangle. Here's theta. So secant theta, that's going to be hypotenuse over adjacent. So here's hypotenuse, here's adjacent. That means this missing side is rad 25x squared minus 121. Always check. I like to check here. Was that in my original integral? Or have I screwed up in some way? Look, there it is in the denominator. So things are good. Okay, cool. Here we go. We've got a 1/5. It's an ugly looking 5. Come on, pull it together, 5. ln, absolute value. Secant theta, we already know. It's 5x over 11. Plus Tan theta, that's going to be opposite over adjacent, so that's going to be radical 25x squared minus 121 over 11 plus c. Okay, we're going to do the same thing with the natural log and the constant. Do you remember what it was? 1/5 ln, absolute value, this is 5x plus rad 25x squared minus 121 over 11 plus c. And then we can use our properties of logarithms and rewrite this as ln absolute value 5x plus rad 25x squared minus 121 minus ln of 11, like that, plus c. And then you just absorb that negative ln of 11 over 5 into your constant, and you can write your final answer as 1/5 ln absolute value 5x plus square root 25x squared minus 121, close up that absolute value, plus k, where, what was k? K is equal to c minus 1/5 ln of 11. Okay, that's totally fine if you don't like putting a k for the constant in your final answer, you know, because the book will probably have a c. Then you can always go backwards once you realize you're going to do that and change all of these to k. And then say, now this is c, this was k. I mean, it doesn't matter. It's just if you want plus c to be how you write the final antiderivative. Okay? Whatever. That looks so messy. I'm just going to pretend we were happy with the k. Something different, eh? It doesn't matter. Check with your instructor. If they're super picky, then do what they want to make them happy. Okay? Good. I got one more for you. I know we've done all three cases, but sometimes you have to be a little bit fancy, schmancy, and I didn't show you any definite integrals, so I thought it was time. Okay, here's one of my favorite ones. If you're in my class, I've put it on a test many a time, so listen up. I'm not making any promises, I'm just saying. Example 4. Integral 0 to ln of 3 e to the x dx over radical e to the 2x plus 1. I'm going to give you a big hint that you're going to u sub first and then use a trig substitution, okay? And to inspire you maybe with the u sub, let's rewrite the denominator. We've still got e to the x dx in the numerator, but downstairs I'm going to write square root e to the x squared plus 1. Can you see what a good choice for u would be? Yeah, we should let u equal e to the x, because then du would be e to the x dx, which we have right here. Wonderful. So now we have du over radical e to the x is now u squared plus 1. And yes, we must switch our limits of integration immediately. So u of 0, the lower limit, is going to be e to the 0, which is 1. So this is 1. And then upper limit, u of ln of 3 is e raised to the ln of 3, which is just 3. Lovely. Okay, cool. So what substitution should we make? Which case is this? Notice under the radical, we've got u squared plus 1. Yep, as soon as you see its addition, it's tangent time. It's tangent time. So we're going to let u, right, we're not working with x's anymore, equal tan theta. So then du would be secant squared theta d theta. Okay. Now let's rewrite everything. So in the numerator, instead of du, I'm going to write secant squared theta d theta. And then underneath the radical, I've got u squared plus 1, which is tan squared theta plus 1. Again, switch your little limits. Pronto, people, pronto. So these limits are for u. Let's look at the lower one. So this means u is equal to 1. So 1 is equal to tan theta. Can you think of when tangent is equal to 1? Why, yes, it is at pi over 4. What about the upper limit? Perhaps it's making you nervous. 3 is equal to tan theta. Is that a value that we easily know from our unit circle when tangent theta is equal to 3? No. So right now I'm just going to replace it with tan inverse of 3. Okay. Good. Okay, so let's see how we can further simplify. Underneath the radical is where all the action is. Tan squared theta plus 1, that's secant squared theta. But then I'm taking the square root of that. So now I'm going to have integral from pi over 4 to tan inverse of 3. And we've got secant squared theta d theta over secant theta. And secant's going to cancel out. I'm telling you, you need to memorize antiderivative of secant theta. Look how much it's come up already. So pi over 4, tan inverse of 3, and we've just got secant theta d theta. So we know that's ln, absolute value, secant theta plus tan theta, and we're evaluating this from pi over 4 to tan inverse of 3. Okay, here's my favorite part. So now we've got ln, absolute value, substituting in tan inverse of 3 for theta. The first expression is going to be secant of tan inverse of 3 plus tangent of tan inverse of 3 minus ln, absolute value, secant of pi over 4 plus tangent of pi over 4. All right. Don't get your calculator out, please. Don't even think about it. Secant of tan inverse of 3. So remember, tan inverse of 3 represents some angle theta. It is triangle time. If it's not some value that we know from the unit circle, then you have to draw a triangle, right? Like 3 is not one that we've memorized. Okay. So tangent is opposite over adjacent. So tangent of theta is going to be 3 over 1. That means the hypotenuse is how much? Rad 10. Bravo. So secant of tan inverse of 3 is saying what is secant of this angle theta? So secant is going to be hypotenuse over adjacent. See, you can do it. So this is ln, absolute value. Secant of theta would be rad 10 plus, you don't need a triangle for this one, tangent of tan inverse of 3 is just going to be 3 minus ln, absolute value, secant of pi over 4. Well, cosine of pi over 4 is rad 2 over 2 or 1 over rad 2. And I actually like thinking of it as 1 over rad 2 better because secant theta is the reciprocal of cosine theta. So 1 over rad 2, I can flip that easy squeezy in my mind. Now it's just rad 2 plus tangent of pi over 4, that's 1. Okay, and in this case, see how we have no variables in our final answer because we evaluated a definite integral, right? So we don't have a plus c, we don't have variables, this just represents some number. And I'm noticing these values inside the absolute value bars, they're not negative. So I can switch out and just write everything with parentheses instead of absolute value since they're not necessary. So ln rad 10 plus 3 minus ln rad 2 plus 1. Okay? If you're feeling overly zealous, then maybe you're going to, I don't know, combine the logarithms, rationalize the denominator. It's getting a little carried away, if you ask me. So I say let's stop here, box it. We're super proud of ourselves. That's a nice looking answer. And hopefully you found this video helpful since we worked through some more tricky techniques. and examples. So if you found the video helpful, please give it a thumbs up, subscribe if you haven't already, and stay tuned. I'll do more partial fractions examples coming up soon, integrals involving partial fraction decomposition, since I know that's another tricky topic too.